Hey everyone! Today, we're diving into a very exciting coding interview problem. Finding the longest palindromic substring. Sounds simple, right? You're given a single string, and your job is to find the longest palindrome hidden inside it. But before we jump in, let's make sure we're all on the same page. What is a palindrome? A palindrome is a word or phrase that reads the same forward and backward. Think of the word level. If you reverse the letters, it's still level. That's a palindrome. So how do we actually check if a string is a palindrome? Easy. We can use the two-pointer technique. You put one pointer at the start, another at the end. Move both pointers toward each other, one step at a time. If at every step the characters match and they meet in the middle, boom! That's a palindrome. Since we're scanning the string once, this check takes linear time, ON. Alright, now that we understand what a palindrome is, let's get back to our main challenge. We're not just checking if a string is a palindrome. We need to find the longest substring inside the given string that is a palindrome. What's the brute force way to do it? Well, we could go through every possible substring and for each one check if it's a palindrome. But here's the thing, there are ON squared substrings in total. And for each substring, checking if it's a palindrome takes ON time. So overall, the brute force approach runs in ON cubed time. Not ideal, especially as the string gets longer. So let's pause here. Now that we know the problem, the brute force solution, and why it's not efficient, alright, now let's talk about a much smarter way to solve this problem. Here's the idea. We go through the string one character at a time, and at each character we assume it could be the center of a palindrome. From that center, we expand outward, checking the characters on the left and right as we go. Let me show you what I mean. Imagine we're at the letter B. We place two pointers, left and right, both on that B. Now, since the characters at both pointers match, we expand outward. Move left one step to the left, and right one step to the right. Now we're at two A's. Still the same? Great! We expand again, but now the characters don't match. That means we stop expanding. The portion we just checked, that's a palindrome. And here's the cool part. Once the characters don't match, we know there's no need to check any further from that center. We've found the longest palindrome centered there, and we move on. But hold on, there's a catch. This approach only works if the palindrome has an odd length, because we started from a single center character. What about even length palindromes? There's no single center, so we have to do one more thing. For each position, we also try expanding from two characters. That means placing the left and right pointers between two letters. This way, we cover both odd and even length palindromes. Sounds a bit complex? Don't worry. Once we walk through the full cycle, it'll totally make sense. Let's dive in. Okay, let's walk through the full process together. We're going to scan the string, BABBAD, and at every character, we're going to assume, what if this is the center of a palindrome? Let's start from the first character, which is B at index 0. Let's check the odd length case first. We place both the left and right pointers on the same character, the B at index 0. Since the two characters are obviously equal, we have a valid palindrome of length 1. We try to expand outwards, move the left pointer to the left and the right pointer to the right. But the left pointer can't go past index 0, so we stop here. Now let's also check the even length palindrome for this index. For this, we place the left pointer at index 0 and the right pointer at index 1. The left character is B, the right character is A. They're not the same, so no palindrome here. We're done with index 0. Now let's move on to index 1. First, we check for the odd length case again. We put both pointers on the same character, A. That's a valid one-letter palindrome, but it's the same length as the one we already had, so we don't update our longest substring yet. Let's try expanding outwards. The left pointer moves to index 0, B, and the right pointer moves to index 2. They match! That gives us BAB, a longer palindrome of length 3. This is better than our current max. So we update our max substring to BAB. We try expanding again, but the left pointer would move to -1, which is out of bounds, so we stop expanding. Now let's check the even length case for index 1. We place the left pointer at index 1, A, and the right pointer at index 2, B. They're different, so again, we skip. Moving on to index 2, the character B. Let's start with odd length again. Pointers on index 2, both on B. We expand left to index 1, A, right to index 3, B, but they don't match. So that's it for the odd length check here. Now we try the even length case. Left on index 2, B, right on index 3, B. This time they match, so we expand. Left goes to index 1, A, right goes to index 4, A. Still matching, so we now have the palindrome ABBA, which is 4 characters long. That's longer than our current max, BAB. So we update our max substring to ABBA. Let's try expanding again. Left moves to index 0, B, right to index 5, D. But they're not equal, so we stop here. We continue this exact process until the end of the string, checking both odd and even length palindromes at every index, expanding as long as the characters match, and always updating the result if we find something longer. And that's it! By the time we finish scanning the string, we'll have found the longest palindromic substring. Now, let's quickly talk about the performance. At each character, we do 2 expansions, one for odd, one for even. And in the worst case, each expansion can go across the entire string. So the time complexity is O(n)², much better than brute force, and totally acceptable for interview-level problems. Now, let's turn all of this logic into clean, simple Python code. Alright, now let's turn everything we've learned into code. First, we'll define a helper function called expandFromCenter. This function takes 3 arguments, the string s, and 2 pointers left and right. What we want to do here is keep expanding both pointers outward as long as they're still within the boundaries of the string, and the characters at both ends are the same. So inside the function, we'll use a while loop. As long as left is greater than or equal to 0, and right is less than the length of the string, and sleft equals sright, we keep expanding. Each time, we move left 1 step to the left, and right 1 step to the right. When that condition breaks, we stop. But we've gone 1 step too far, so we return the substring from left +1 to right. That gives us the longest palindromic substring centered at that point. Now let's implement the main function. We'll call it something like longest palindrome. Inside, we'll define a variable to keep track of the result. Then we loop through every index in the string. For each index, we check 2 cases. First, we assume the palindrome has odd length, so we expand from I to I. Second, we check for even length palindromes, so we expand from I to I+1. Each time we get a candidate substring, we compare its length to the current longest. If it's longer, we update our longest. After we go through the whole string, we simply return the longest substring we found. And that's it. Pretty simple, right? It's efficient, elegant, and great for interviews. Now that we've seen the 2-pointer expansion method, let's take a look at another powerful approach to solving this problem: dynamic programming. Just like any DP problem, the key idea here is to break the problem down into smaller subproblems, solve those first, and then build up to the final answer. Let's walk through how that works. We're still working with substrings of the input string, but this time we're going to use a 2D table. Each cell in this table represents a substring. Let's say we have 2 pointers, left and right. These mark the start and end indices of a substring. So if left equals 1 and right equals 3, the substring is ABB. If left equals 1 and right equals 4, the substring is ABBA. Now here's the dynamic programming insight. If we want to know whether ABBA is a palindrome, we can ask two questions. First, are the characters at both ends are the same? Second, is the inner substring a palindrome? If both are true, then the whole string is a palindrome. And here's the beauty of DP. We've already solved that smaller case, so we can just look it up in the table. Specifically, one row down and one column left. The bottom left cell. Let's walk through the full setup. We'll create a 2D Boolean table. Let's call it DP. DP left, right. Will be true if the substring from left to right is a palindrome. First, every single character is a palindrome by itself, so we mark all DPI equals true. Also, we won't bother filling in any DP left right where left is bigger than right, because that's not a valid substring. Now here's how we'll fill the table. Since we need to look at the bottom left cell each time, we'll fill the table from top to bottom and left to right. So we'll start with right from the start of the string and move forward. And for each right, we'll scan left from 0 to the right. For every pair left-right, we check. Are S left and S right the same? If they're not, that's it, not a palindrome. We mark false and move on. If they are the same, then we look one level smaller. Is DP left plus 1, right minus 1 true? If yes, then this larger substring is also a palindrome. And whenever we find a true, we check, is this longer than our current max substring? If yes, we update it. We keep doing this for every pair. And when we're done filling in the table, we'll have the longest palindromic substring stored. For our example string, BABBAD, this approach would correctly find ABBA as the longest palindrome. So, same result as before, but a completely different approach. Now, let's take this logic and turn it into Python code. Alright, let's implement this dynamic programming approach together. We'll start by initializing a few things. First, we need to know the length of the string. Let's call it n. Then we create a 2D table, DP, with n rows and n columns. Every cell will start as false, because by default, we assume no substring is a palindrome. Now, there's one thing we know for sure. Every single character is a palindrome by itself, so we loop through the diagonal of the table. For every index I, we set DPII equals true. That's our base case. Next, we'll start filling out the rest of the table. For every right index from 1 to n minus 1, we'll move left from 0 all the way to right minus 1. At each point, we check, are S left and S right the same? And is the inside substring DP left plus 1, right minus 1 also a palindrome? Now, here's the thing. If the characters match and either, first, the gap between them is 1 or 2, which means the middle part is empty or just one character, or second, the inside substring is already marked true in the table, then we mark DP left right equals true. And if this new palindrome is longer than our current longest substring, we update the result. We keep repeating this for every pair of indices. By the time we've filled the table, we'll have found the longest palindromic substring. Now let's talk performance. We're checking every possible pair of left and right, so the time complexity is O(n squared). But unlike the previous method, we're also storing results in a 2D table, so the space complexity is also O(n squared). That's one trade-off. That's why, in practice, the center expansion method is usually preferred. It's simpler and uses constant space. Still, understanding this dynamic programming approach is super valuable. The core idea, breaking down a big problem into smaller ones, is something you'll see again and again in algorithm interviews. Oh, and one last thing. There's actually a linear time solution to this problem too, called Manneka's algorithm. It's quite advanced, and you won't be expected to use it in interviews, but if you're curious, definitely look it up. All right, that wraps up our lesson on the longest palindromic substring problem. We've seen multiple ways to solve it, compared their trade-offs, and hopefully built up your confidence to tackle similar problems in the future. Great work today, and I'll see you in the next one.